To introduce the problem we're trying to solve, we don't have to look much further than the scene here, which is one of the many plastic waste patches that roam the oceans today. Tens of thousands of tons of plastic are entering the environment yearly, with a total of nearly 70 million tons of PET being produced globally each year. Not only that, but current plastic recycling methods at large are only about 21% effective due to their nature, which means that only 1 out of 5 plastic bottles you throw in a green bin are actually going to be repurposed. To make matters even worse, those new plastic things that are being produced by the recycling methods are the products of what is called downcycling, which is where you take one product and you turn it into a product of lesser quality. That lesser quality, of course, being that they are not as easy to recycle. So, for example, turning a heap of plastic bottles into a pair of shoes. The shoes are not nearly as recyclable and repurposable as the bottles beforehand, thus we've downcycled them.
Right now, another way to look at the problem of plastic is seeing the single stream economy of how it works, where it takes oil and transforms that into the monomers that are made into PET, which are ethylene glycol, or EG, and terephthalic acid, or TPA. When it's then polymerized into PET, where does that plastic go? Well, it goes into the environment, landfill, or it's incinerated or downcycled, all of which are still have the plastic there, and it's still what is going to happen to the PET? Well, that's where we come in, where we take a recycling method of closing the loop. This then takes out the petroleum processing of we don't need any more oil for this, and takes away the problem of taking that PET and putting it into the environment, where we're able to close the loop and be able to use the same PET over and over again. Right now, this is also better than other recycling methods due to the fact that it's a cleaner cut on the monomers, where ethylene glycol and terephthalic acid are better in that regard.
For the process, synthesis, and description, the team decided to split up these descriptions from the upstream and the downstream process. For the upstream, we decided to recycle 10 tons of PET plastic per month based on economics for the Lamar County area. For the upstream process, we have to extrude the PET solid waste at 245 degrees Celsius with a twin screw extruder, and this is to make the plastic amorphous and easier for the enzymes to digest. Then that amorphosized and extruded PET will go into a bioreactor containing the ICCG enzyme, which degrades the plastic with sodium hydroxide media. And the parameters for this bioreactor will be a pH of 8, 72 degrees Celsius, and 4 milligrams of ICCG enzyme to 1 gram of PET. These parameters were determined by testing on campus and will be explained later.
So, moving on to the process synthesis for the downstream part of the system, we move on to point 3 here, which is an activated carbon column. And this is going to be receiving the product stream from the bioreactor, which is going to pick up impurities such as solid PET and their oligomers, enzymes from the broth, as well as any other impurities that are organic compounds such as dyes that could have been in the bottles. Then that's going to feed into point 4 here, which is a crystallization tank, and it's where the first separation of one of the monomers is going to take place for TPA. Crystallization tank is going to be receiving sulfuric acid in order to lower its pH and have that terephthalic acid crash out of solution in crystal form and be easily separable from there. And that's where that process stream in the green is going to. And now the product stream is going to feed into the basic mixing tank, which is where we're going to return in a caustic phase the pH of the stream back to its original, or rather a neutral pH, around 7 to 8, depending on the process conditions, where we're going to be adding magnesium hydroxide as a base to counteract the previous addition of sulfuric acid. And then after that, we're going to go into a different phase where we have ammonium hydroxide added. As the problem is, when you add the magnesium hydroxide and the hydroxide groups break off and raise the pH again, what you're left with is the magnesium salt. And so in order to regenerate that magnesium to repurpose for this process, which is one of the alternative separation methods we've looked into with the recycle stream on the mixer, we're going to add ammonium hydroxide as seen in part 5 as well, where we're going to have that hydroxide from the ammonium hydroxide regenerate the magnesium hydroxide, which we can then put back into the process. And as a byproduct, which is what we were trying to replace, have ammonium sulfate come out as a solid crystal as well, as opposed to what we were doing before. We were producing sodium sulfate, which was a not incredibly useful byproduct and essentially was waste. However, ammonium sulfate is a sulfur fertilizer, so this byproduct is something we can also look into the future in order to look at the economics of selling such, as well as its other uses that we could take it for. Now, moving on, that feeds into the entirety of section 6, which describes the ethylene glycol recovery. And we start off with 2 mixing tanks, the bond EG tank and the acid mixing tank. So in this first tank, the product stream is going to be fed in, and decorated silica microparticles that have boronic acids on its surface are going to be added to the process stream in the mixer. And at the right conditions, with a buffer solution and or base added in order to raise the pH to a basic condition, we're going to have those reversibly pick up the ethylene glycol and then move on into another mixer to get rid of that stream, potentially a centrifugation, in order to recover those particles that are now holding on to the ethylene glycol from the solution. And we're going to add that to another tank afterwards, which is the acidic mixing tank. And in acidic conditions, the reversible bond will be undone, and that will drop off the ethylene glycol into a solution that is far more concentrated in ethylene glycol than it was before, as the feed stream going into the first mixer is typically going to be either 1/3 or even 1/10 ethylene glycol. So that's going to help purify it and separate out the ethylene glycol, which is then going to go into a final separator and recover our EG, which is the second green box.
Like I said earlier, we are going to describe our testing to develop our process synthesis diagram. For the upstream, we did testing to determine the optimal parameters to produce terephthalic acid, also known as TPA, and ethylene glycol, EG. And these are the monomers that will help close the loop to recycle PET bottles. We did this by varying the enzyme concentration and the temperature of degrading the plastic. And you can see this in the image here. We have 6 different variations of these parameters. And we ran these for about 24 hours to determine the maximum production of TPA over that experiment. We determined the TPA production with HPLC, or a high performance liquid chromatography, with the ARC lab and the chemistry department. From this testing, we determined that 72 degrees Celsius with 4 milligrams of ICCG enzyme to 1 gram of PET was the most optimal, based on it having the most production of terephthalic acid produced compared to the other parameters. And you can see here in the image where we have little fine lines of PET plastic, and this was the most degraded plastic we had compared to others where we had more folded plastic. And
so as for the downstream testing that we did for the process synthesis, what we looked at was determining the validity of the alternative separation methods that we proposed for both monomers, which are TPA and ethylene glycol. And so for that first half with TPA, what we ended up doing was attempting a calculation-based pH reduction from 8 to about 3 in order to have that solid TPA crash out of solution and be easily recoverable with filters. And then the second half of that was ethylene glycol, where we took our kind of proof of concept experiment for boronic acid decorated on silicon microparticles, which you can see in the bottom left with the microscopy image, and take those, put them in the correct conditions with a solution, in a buffer solution, and have that reversibly pick up ethylene glycol, move it into a second solution with different conditions, which are more acidic, and have it drop them off so it is much more concentrated, as the stream going in is going to be mostly water. And the results of which were that the crystallization, as expected, was easily doable, and the TPA crashed out, proving that our practical experiments did produce the monomers. And that in a similar way, we took a pilot solution for the ethylene glycol, added the silicon microparticles, had those centrifuged out, and added into a separate solution where we were able to successfully separate all of those things from each other, and ideally, ethylene glycol was sitting.
Safety of our project. At the scale we were at, there weren't too many concerns. We had a few chemical hazards with our reactions: TPA, ethylene glycol, and boronic acid. These 3 were used in our reaction and our separation process. So just being aware of what those would do if inhaled or orally ingested. We consulted the SDSs and our advisors, and then there was also a biological hazard with our enzymes that were used. The same thing, one of our grad student advisors works extensively with enzymes, so he was able to advise us on how to properly handle these. The biggest safety concern for us was the extruder. Our PET had to be thermally pre-treated before, and this meant heating it up to 245 degrees Celsius, so very hot. And just being aware, we got trained by a grad student who used this machine, and he taught us how to wear the right PPE, clean it, and run it. So yeah, some of the solutions for our safety were to wear PPE whenever we're in lab, and if this process gets scaled up, use process control sensors for the temperature, and then also to evaluate the integrity of the tanks that we would use at a large scale, because we do use some corrosive chemicals. As far as sustainability is concerned, both of our process and the current process start with plastic collection. From there, ours differs. We use enzymes to degrade the plastic polymer into its two monomers, ethylene glycol and terephthalic acid. After this, we use a precipitation reaction to crash out our TPA, and then use boronic acid decorated microparticles to separate out our ethylene glycol. After that, the two monomers, ethylene glycol and terephthalic acid, are repolymerized into bottles, closing the loop on the circular economy. This is where it differs from the current process, which would put those bottles into recycling centers or landfills. So the pros of our process are that it actually recycles the PET instead of downcycling the plastic like is done in current recycling plants. If we close the loop on the plastic bottle, it'll increase the profit of the bottle over time. And then since we were able to find some novel separation techniques, it will reduce the emissions caused from the current distillation separation that the current art is using to acquire the ethylene glycol.
Our customer outreach was to 4 major different groups of people, including citizens, different recycling centers, EcoCycle, and county representatives. When we did this, we first looked at citizens and see recycling habits in Larimer County, and especially in Fort Collins. And we learned from this is how much people are willing to spend on recycling, and as well how people recycle in general. From this, we were able to talk to people such as County Representative or County Commissioner Kristen Stevens. She gave me a lot of information, a lot of contacts to talk to, and she also told me about the plans of recycling here in Larimer County. She was very useful and really pointed us in the right direction. From here, we were able to also learn more about the plans of Larimer County going forward, and to know a little bit more about the new landfill here in Larimer County. After that, we were appointed to talk to the solid waste management here in Larimer County, and talking to them, they got a lot of information and a lot of new people to talk to from there. We were also able to validate some of our numbers and understand how recycling works in Colorado, where a lot of plastic isn't recycled per se, but cardboard and glass are major recyclables here. From here, we were able to talk to people at EcoCycle. That's another group based in Boulder that we were recommended to talk to. These gave us a lot of a deeper understanding of how recycling works and how policies are being made. Bills passed, such as the circular economy bill, was one of the things EcoCycle put on and did a great job of getting passed. We were also able to understand what Recycle Colorado is, which is a large group of companies here that are all a part of learning how to recycle better in Colorado and learning about how to deal with the new laws in order. From this, we were able to look at the market analysis. This is a different way to look at it, where we have 2 companies that are your typical recyclers, such as Republic and Waste Management. These ones pick up trash, but they don't do a lot with their trash when they pick it up. It's basically just like going to a landfill. For example, Waste Management picks it up, but they separate it, so they're a little bit better. We also have a scoring column where you can see 10 being the best and 0 being the worst. Covanta and Carbios are 2 companies that take these recyclables and they do stuff with them. For example, Covanta normally incinerates them or downcycles them, which is better than doing nothing with them or putting them into the landfill. Carbios is very similar to what we are doing, where they're an enzymatic company that sells enzymes to other companies such as Covanta, and they are able to use these enzymes to make different products, such as the ethylene glycol and terephthalic acid that we're also looking to do. For our project, however, we're doing something a little bit different where we're charging a subscription fee to pick up trash and then recycle this. This is the entire circular economy, which is a lot better than just specializing in one of the areas. As well, another important part to look at is the number of years in service, where we're a very new company, but we're looking to make a big splash, especially in Colorado with all these new bills being passed. It is very plausible for us to be able to do this.
When working through the techno-economics of this project, we started with the raw materials, which come in at around $32,000. For employees, we are going to have 1 trash collector, 3 operators, and 3 engineers. Their monthly salaries combined will be around $39,000. And then our products, which are TPA and EG, will come in just under $400,000. So subtracting our raw material and employee costs, we'll have a profit of around $300,000. The infrastructure to build this plant, including the land, the bioreactors, the extruder, things of that nature, will come in just above $1 million. And this is all on a per month basis. We based our raw materials off bulk prices. So that would be train cars of chemicals, things of that nature, and they do not include shipping at this point, just because it fluctuates so much. Our raw material cost may be able to be decreased in the future. We are accounting for having to buy or make our enzymes new every month. But since they have a HIS tag, they are able to be extracted using a nickel column, but we did not have time in the scope of our project to test their durability or robustness. And there's also an option to reduce our infrastructure cost if we were to merge with an existing recycle or composting company. This would allow us to use their existing trucks and logistics systems, which would be a great help. For a further dive into our techno-economics, like I said, our infrastructure cost will also be our initial investment. So we would be looking for around $1 million to help start our plant. Our return on investment is incredibly high. I will get into that in just a second. Our payback period would be about 1/3 of a year, and then our yearly profit would be closing in on $4 million at 3.7. The reason we think our ROI is so high is mostly due to our low raw material cost and our high product sale cost. Like I said previously, our raw materials are sourced at bulk pricing, so they're very, very small, on the order of cents per kilogram of materials. But since we are using a more greener recycling method, we thought it was fair to increase the cost of our products. So what we did was look at our one of the current chemicals that has green and brown types, which is hydrogen, and we took a ratio of the two. That came in at green hydrogen being about 7 times more expensive than brown hydrogen. And since our TPA and ethylene glycol are green, we multiplied their bulk price by 7 to get our sale price. And so this is why our return on investment is so high.
For future works and thank yous, we first have to investigate the feasibility of recycling enzymes with a nickel resin column. And this is because, as Eric said, it could possibly reduce our costs and our waste of the enzymes by capturing them with a HIS tag and then reusing them in 1 or 2 more processes of degrading the plastic. Another option is to investigate possible alternative enzymes, because protein engineering is ever growing to make these plastic degrading enzymes more stable and work at higher temperatures. And then to compare purified enzymes to supernated enzymes. And this is because purifying enzymes is a very expensive process, where if you use supernated enzymes, there is more E. coli or cells that would be lysed out of, but if it's equally efficient, this could reduce our cost. The full experimental run to go through all the processes will be a final step to make sure our process is feasible and economical at a large scale. Our thank yous go to Dr. Margarita Herrera Alonso. She's been our advisor throughout this whole year. Bert Vermeulen to supporting us through the venture project and supporting us with funding. Andy Trimmer, who is our mentor through the venture project and has been very helpful in the market analysis. Jacob DeRue, who's a PhD candidate. He's been a graduate mentor to help us throughout the process. Jamie Cusciero is a post-grad student that helped us with the HPLC testing. Carla Curena Hernandez, she helped us in the Herrera lab. And then members of the National Renewable Energy Laboratory donated the enzymes, and then the histones lab who purified our enzymes, and then the chemistry department in the ARC lab to use instruments to analyze our data.